So here's the title, and we got a few co-people here. Kyle is one of our lightning experts, and a couple of folks from the nearby WFOs. So if you come out with nothing else out of this whole thing, it's kind of want to point out that of all the types of tornado genesis that we have, non-supercell tornado genesis is, I think, the most highly correlated with storm updraft, and it's far more so than supercell tornadoes. And because total lightning is specifically in-cloud lightning is also highly correlated with updraft strength, the thought is that maybe monitoring this total lightning behavior may help to give us some hints that perhaps could aid in warning for these types of tornadoes, which are tricky to warn for. So my motivation is way back in the 80s, actually a little bit after I came to NCAR, we started looking at these non-supercell tornadoes, and so that's where I kind of became familiar with this. And certainly they're much more difficult to warn for than I mean, it can be difficult to warn for because the signals are kind of small on the radar, they're too far away, and they start from the bottom generally up, and so you can overlook them with the radar if it's 40 or 50 miles away. So it gets tricky. And here's just a little bit of review. Ray Brady, who's I think still with Binghamton WFO, but he worked with us out here in Boulder for a while. We studied this one tornado in near Denver back in 1987, and we came up with Doppler radar, I should say, which was the first time anybody had studied a non-supercell tornado. Actually, it was 1985 with a Doppler radar, and we came up with this schematic where, picture a boundary, and some of these boundaries will have these circulations just sitting around on them, and then if you happen to position an updraft over one of these circulations, well, you can be stretched in the vertical, and then bingo, you got a tornado. So the difference between this and a supercell is that we have essentially the vertical vorticity already, the vorticity already aligned in the vertical for these kind of tornadoes, just waiting to be stretched. Whereas in the supercell tornado, of course, the cloud itself has a lot of rotation, but how do you get that rotation at the ground? So much more tricky in supercell. So often these will have no pre-existing mesocyclone, which makes them, hard to predict. Now, typically they are pretty weak, but we have seen EF2, and even one time in the Denver area, we had a little EF3 damage of a non-supercell outbreak. So this became known as a land spout, and actually Howie was the first person to make that name in the 14th conference on severe local storms. He didn't have a good radar study of it, but he noticed there were some other tornadoes that once in a while showed up when he went out to study it. And then Wakamoto and Wilson had a really good paper that looked at a lot more cases from a big field program we had in 1987. And their schematic is shown here. It's a little curious because, I don't think the clouds, they look kind of smaller, and typically I think they are much bigger. Anyways, the motivation for this study is that both the Boulder and Cheyenne WFOs were involved in this tree-goes-are testing for the GLM, because we have a land-based network that does in-cloud lightning called the Colorado Lightning Mapping Array. And I haven't done it in a while, but I used to do quite a few shifts at the forecast office. So then I'd give a talk once in a while at their workshops. And I was attending their April spring workshop in 2013 when Jeffrey Stano, who was still is a big lightning expert at NASA Sport, gave a talk on total lightning. Now, he talked about some of the sports studies, and maybe you've heard of some, and they often, they made some claims with supercell tornadoes, and I think they backed down on a little bit, but there's certainly, I think, a good correlation with lightning jump and severe hail. But the supercell tornado connection, I think, seemed a little more dubious, but I wondered about non-supercells. But before we get to that, you may wonder, and I've thought about about this a little bit. What about other kinds of tornadoes besides supercells? And we had a presentation recently, which is recorded version is down here on our visit page. I think it was a forecaster from Alabama, one of the WFOs there, and he talked about QLCS tornadoes and showed some lightning data that was kind of intriguing. And if there's any tornado where the updraft may also be pretty important to the actual tornado genesis, it could be these QLCS tornadoes. But today we're going to discuss simply the basic non-supercell tornadoes. So shortly after Jeffrey gave his talk, I was working a shift on this day in June at the Boulder WFO, and we had this non-supercell tornado that actually hit the airport, which it's really the only one that's come onto the airport grounds. And there's, of course, there were a lot of pictures. And so we had tremendous radar coverage. And obviously, it was quite close to the radar. In fact, we had to use another radar to get better coverage of the upper part. And then in a bonus, we actually had two cells that formed along this boundary that we call the Denver cyclone. And one of them formed a tornado and the other did not. So we're kind of able to compare the two of them. So what we did with this data set, using Jeffrey's help, was look at the lightning behavior and look at the radar behavior, kind of like we did with the first non-supercell tornado we examined, and then look at these time-height diagrams. I'm going to show you this sort of thing. This is experimental stuff, but you can do something like this in real time on AWIPS as well. We'll talk about that in a bit. Here's the track of the actual tornado date. Bargain book put this together. So we were watching this closely, and it finally touched down just south of the airport. If you've been to DIA, the terminal's up here. So it was heading right across the airport grounds. There was a AWOS station that recorded a wind gust of 109 miles an hour. So it's not going to, it's not going to destroy the airport, obviously, but with all the glass and the terminals and everything, it certainly presented a hazard. And so somewhere in this path, we were in constant contact with the airport, and they decided they would actually have everybody take shelter. And this is what the impact was. This is actually a picture from that time. I was telling a person who took this last week, who knows, this could be what the airport looks like now, but where did everybody go? Well, this is amazing that everybody was able to go into a shelter. And I don't know if you've been to DIA, but here they all are huddled in these train tunnels that take people from the terminal to from the main terminal to the three outlying terminals. And it was remarkable that it only took about 80 minutes for them to get back to normal after this. Anyways, this is what we were looking at the time. We had a situation awareness display, which looked at the ground-based network, and we had source points were pictured. And what I've done here is have the display, and it also showed a vertical extent, which cannot get, of course, in GLM. And then I've blown up the area around DIA. So DIA itself is here. And the cells we're going to watch here, and then we're going to watch one closer to DIA. So we have these two cells, and I've shown them here. And at first, the southern one starts growing pretty rapidly. There's a composite reflectivity on the left. And remember, the tornado happened, it happens in a little while yet. It's not anywhere near, about 2021, I think. So this first cell really started to grow rapidly. And in fact, we put out a warning on that cell, which did not verify. But then the northern one takes over with really strong growth in the amount of in cloud and basically total lightning. Most of this was in the cloud at the time. And so what we did later, and then we had the tornado forming about here. So what we did later was to have Jeffrey was able to isolate both these cells, kind of put a circle around them. They don't move very fast. There's not much shear this day. And then we calculated the amount of lightning in each of those circles. Now, of course, we didn't need total lightning for this storm. This is obviously, so as I said, close to the radar. Here's the signal from the TDWR, for example, which is extremely excellent signal. But it was fascinating to watch. I remember they were watching the radar, and I was watching the lightning, and I kept saying, wow, this thing has really got a lot of lightning. It really got a lot of lightning. So it was fascinating to see, especially only 2 months after Jeffrey's talk. lightning trace. So what I'm going to contrast here, the southern cell didn't have a tornado, and the northern cell did. Now, the first thing that I noticed when we looked at this data were these low points. We wondered about those. So Jeffrey took a look at this, and he noticed that the ground-based network actually had some sensor trouble during that time. So we don't know the behavior during this time. For all we know, it could have been ramping up. What we do see is two things. The amount of lightning in the tornadic storm is about twice as much as the non-tornadic. You see how it settles down in that one. And then there's this peak that happens right before the confirmed tornado touchdown. So this was viewed, we viewed this as kind of a positive development. We had more lightning in the one that had the tornado, and we also had what appears like a bit of a lightning jump. Unfortunately, very close to the tornado, so the lead time wasn't all that great, but it was a positive, we thought. Now, we also looked at this in relation to the rotational shear, which is something we did for the study in 1985. And what you typically see in these non-supercell tornadoes is, again, you have the low-level rotation, and here we see some lightning activity pick up here, and the reflectivity also picks up, but it kind of is a rapid growth in the reflectivity, in the velocity, increase in the velocity and increase in the depth of this rotational shear just before the tornado. You see it kind of builds up from low levels. Now, if we look at that also in relation to the reflectivity, again, initial reflectivity builds up and then more as we get closer to when the updraft strengthens. I want to also point out, of course, that the freezing level is pretty important to note. A couple of southern WFOs who have taken this have noted that, well, they never saw any lightning, and of course some of their cells can even produce a non-supercell tornado without ever getting above the freezing level. For us, that's never a problem. Even though it's fairly high, our cloud base is typically pretty high. But you do have to get a cloud above the freezing level for any of this to be important to get the mixed phase. So this was the southern storm, and you can see that quite a difference here, that the reflectivity builds up just as the other one, but then it kind of flattens out, and the lightning, after increasing, then kind of goes at a steadiness. And that kind of agrees with the way the cell behaved as well. And in terms of the velocity, it had a nice increase at first, but then again, it kind of holds steady, and we're kind of left with this weak mid-level rotation. So what we concluded from all of this, while only one case, we were able to contrast a tornadic with a non-tornadic storm, and it was encouraging to see the jump, even though it was not much lead time, and the fact that there was more lightning with the tornadic one. And then Cheyenne, they had one in July, and Dan and I went up and looked at that. The radar data was just almost useless, even though it wasn't that far from the storm, but the lightning was pretty interesting. And their Sue's thought that there was a nice jump about 10 minutes before. We didn't have the kind of detail we had with this. So what I'll do is I'm going to show you some other cases we've since compiled. And first, one more case using kind of an experimental output, but then we'll look at some stuff you can get on AWIPS. This was a kind of a big outbreak in Iowa, and the initial tornadoes were actually non-supercell types. And this is a plot looking at the lightning with all the tornado tracks. One thing you notice is there's a bunch of little small tornado tracks out here, but almost very little lightning. So we weren't able to look at those very well, but we did look at one of the tornadoes here and then one of the tornadoes right here. And then these actually become probably more supercellular, and you can see quite a bit of lightning, but how that relates to a tornado, we did not look into that. So here's the couple of plots we came up with. The first tornado, we do see a nice jump in lightning. It's kind of coincident. The peak is coincident with the tornado time. Now, one thing I should say, with a study like this, you're kind of at the mercy of is the tornado time accurate? And I think for the Denver, the one we had at the airport, is very accurate. But this one, well, you don't know for sure, but they were visible. So jump, and if this tornado time is accurate, it comes nicely in the 10 minutes before the tornado. So this is about as nice as as we would think we might get. All right, so now we'll switch gears a little bit and look at some other outbreaks, but use some of the stuff you might have on AWIP. So this is a nice little outbreak of non-supercell tornadoes last June, right along the Colorado-Kansas border. And this is how they often look. And again, they might don't see the bottom of these, but it can be dry out here, but the circulation is extending to the ground. And again, some of these won't do much damage, but if they ever hit a trailer park or something, they certainly are capable of even flipping a trailer. The kind of boundary that we had on this day is pretty interesting. It's of course lying about right here. And what you notice, I think this is the most effective kind of boundary, I believe, in producing these kind of non-supercell tornadoes. You have the wind approaching the boundary at an angle from both sides. So rather than straight, west versus east wind, say, this kind of wind often enables you to generate these little vortices. And we had a big outbreak in Denver in 15 June 88, where one of these boundaries was around, reinforced with a couple of outflows that just happened to hit it at this kind of angle, and there were vortices everywhere. And we had 4 tornadoes develop, 3 of them right in the Denver area. It's the biggest outbreak ever in Denver. But it was exactly this type of boundary coming together. So now we'll look at a group of AWIPs for the first tornado. So the first tornado is here. And I don't know, Melissa, if you've ever used this tool, but we're going to show this tool on AWIPs called the AWIPs tracking tool. I believe that's what it's called, tracking mediogram tool. Now, it can be kind of clunky, and it is not necessary to use this tool to think about how you might use lightning data in this way. You can just use a display, like we've shown here, of total flash extent density. Now, one thing we didn't do here, and I'll point it out right now, is that we kind of use the default scale, and you'll notice in the loop that it never really gets very much above these blue colors. So you'll see in some of our other displays that it might be useful in some of these storms that don't produce a lot of lightning to adjust the scale that way, so you can see the differences better. In this case, we put a visible down here. In the loop, this other panel we left blank, and low-level reflectivity. I'll show you some other ones later that might make more sense to put in a 4-panel. But here's the loop. And again, the tornado occurred at 20Z. We're at 1945, 1942. So this is easy to isolate this one. And you see this thing go a little bit up and down. I'm going to try to just stop it for a second. And this is just before, it is around 1951. And it looks like the lightning increased and kind of peaked before the tornado actually occurred. This is, again, we're at the mercy of what did it occur exactly at that time. So here's what happened when we plot this data. Again, we use the mediogram tool. So first what we'll look at is GLM flash extent density. And I think if you use the tool, it defaults to what's called max values. And those are plotted down here. So what is the maximum value amount of lightning every minute in that circle? We kind of found that the sum, which is pictured up here, you can change it to different things, we think works a little bit better. So in this case, we see this ramp up, a pretty good ramp up. It's kind of well before the tornado, though, tornado being over here at 20Z. Now, we should also know, and we show here, that Earth Networks, of course, also has total lightning. So it's kind of funny that the GLM, GOES-R was delayed a few years, and then there's a lot of talk about, we're going to have this total lightning when it finally gets launched. But meanwhile, the National Weather Service did pay for a network a ground-based network from the Earth Networks folks. And so there is this total lightning that forecasters were using before GOES-R even got launched. And our experience is it is a bad network. It is a little different. Of course, it uses obviously a whole different way of traveling. But you can see in this case, I'll compare them in a minute, there was this nice ramp up going a lot closer to the tornado time. So if we compare the two, and this is, Dan and I think is a bit unusual. Most of the time they agree a little better than this, and for some reason they did not agree very well in this particular case. But we have noticed that at times. So the other thing to note about Earth networks, of course, you can, one advantage it has over GLM, the GLM gives you the total lightning, which is in cloud and cloud to ground. Now, in these cases that we're looking at, most of what the lightning that happens before the non-supercell tornado forms is in the cloud, with the total lightning, with the cloud to ground just starting after the storm gets going. And in this case, you see it, but the scale is different. And there isn't all that much cloud to ground lightning, and really no real trend with the storm, which we wouldn't expect. But most of what is made up is the in-cloud lightning. So what this says is I think we can use the GLM with some confidence that most of what we're seeing is in-cloud lightning for these cases. So just looking at the other three tornadoes that occurred, they were kind of in a group, so it gets a little bit harder to use the tool with much confidence. But if you were just monitoring this imagery, you'd be able to see perhaps little maxima showing up that might be useful. But here's what it actually looked like with the GLM versus the Earth networks, again with the sum. Now we're going to look at sum for the rest of these. And not a lot of signals showing up. When we isolated just that one tornado as best we could, then we did get a signal of a ramp up showing up. Now here's another case. This was under upper level low, I think. In Iowa, we looked at these first two tornadoes, definitely non-supercells. Here's the second one over here, I believe. But this first one was interesting. I can write that here. I think it's the first one because we weren't able to use the method for this one because there was actually no lightning with this weak EF0 tornado. We did look at this tornado, which is the one in the picture. And we got, again, we're going to look at a 4-panel. This time, this 4-panel makes a little more sense. You could, perhaps, if you didn't want to look at all the different lightning things, this is total optical energy and average flash area. And I think from what we found, probably flash extent density is the most useful. So you could maybe put composite reflectivity in one of them. But another useful thing to look at might be the RGB, the day cloud phase distinction, which would give you an idea of when the cloud goes from water to ice cloud. So, and that, since that is important for lightning activity, that might be a good choice to look at as well. So here's the loop of this, and again, in this imagery, the tornado, the first one occurred at 21:49. So I'll kind of again maybe stop it for just a brief time. So here's going back a little bit earlier, it's about 21:40, and you can see some pulses of higher right there. For example, in this case, we did adjust the scale, so we're emphasizing some of the lower values, which is kind of important to help you visualize it better. And then we continue on and with this. So what do we see when we plot this up? We have a really nice signal for this tornado in this case. You see the nice ramp up. Again, we're not absolutely sure the tornado formed here, but we can see both, first of all, good agreement, by the way, this time between Earth networks and GLM, both showing a nice ramp up. Here's one other case on the high plains. In this case, several tornadoes again, and they often will occur with more than one. I don't know if you can hear my cat's going wild over here, but this had a boundary similar but not nearly as strong as the boundary you saw for the other case. But I do want to point out in terms of the sounding, the typical sounding for a non-supercell, not a lot of shear, some, but really these winds aren't that strong, but really good instability, which would promote a strong updraft. That's usually necessary, and a boundary. So in this 4-panel, we are showing reflectivity. We didn't use composite, but that might be a better choice in low level. And in flash density, this time we showed total optical. So this is the loop of that one. and again 2146, and then 2203, and this is showing this is about 2146 right here. So you can see that it pulses up kind of nicely, and you do see again, especially when you adjust the scale, you can see some of these maxima show up. So we plot up this one. We got a picture that looks something like this. Before the first tornado, they both showed this increase, continued to increase prior to the second tornado, and then, of course, kept going as the whole complex continued to grow. The New Mexico tornado is embedded with another cell, so it makes it a lot trickier, especially using the tool, but looking just visually. One more thing I should point out, of course, remember with the GLM and when you're using it with Earth networks, that there is the parallax issue with all the satellite imagery and data we use, so that will make things look different from the actual radar. So here's what we saw with this. Again, a pretty nice ramp up leading up to the first tornado, which was then off and on during this entire period. And I don't know what to make necessarily of the up and down in that. The last case we'll close with is a waterspout that came on shore in New Orleans. In this case, the storm was high enough to get certainly above the freezing level. And what's nice about this storm is it kind of goes back to the first one I showed you in the Denver area. We actually have two cells, and this first one is pretty strong, and it has a little rotation. This is MRMS, the level rotation. But it's the second one that actually produces a tornado. So when we look at, they both look pretty strong in reflectivity, and it has some pretty good rotation. But again, no tornado here, and that one kind of dies off in terms of the rotation. And this is the one that produces a tornado at 1855. So let's take and again, then eventually the whole complex grows and we get a lot more lightning. But as the storm grows and starts to produce downdraft, pretty much all the action for a non-supercell tornado is over. So here's what it looked like in terms of the time loop, just using the flash extent density here. So what I'm showing you, again, the tornado is in this area. So this first activity that we see is with the first cell, and you see some lightning, but a lot less than what we see actually right here with the parallax, a lot less than what we see with the second cell. But that's pretty encouraging as well, that we had kind of a null case with that one off to the west, and in this case, produces a tornado. And this is what we saw when we plotted this. Pretty nice, again, nice ramp up, and again, pretty good agreement between the two different sensors that look at total lightning for this particular case. So, putting this all together, we were encouraged to see that a lot of our cases did show a signal. Sometimes it was very short term, and it wasn't always the case, but I think there might be something there. It did depend. We found how you looked at the data in terms of the tracking tool, which again wasn't a necessity to look at it. The tool can be tricky to use, but the fact that the storms in non-supercell days don't move very much makes it easier to use than in other days. In generally good agreement between Earth networks and GLMs. How would you actually use this? Well, certainly you're not going to warn on something based on the lightning alone, but what this seems like, if you were aware there was a boundary around and you're monitoring the thing, it's a kind of a day with weak shear, and if you see a cell rapidly developing along this boundary, whether or not you may or may not be able to see any rotation because you could be too far from the radar. But if you think conditions are possibly right for a non-supercell and you see this rapid growth of lightning coincident with this cell trying to develop, that could be a cell to focus on, and maybe you don't have enough, it might not be wise to go out with a warning, but you maybe put out a statement, or if you get that call, you don't dismiss it. You say, well, okay, I've been watching that cell. So it's a tool to add to the chance of maybe having some chance to warn for these types of things.